let me do review what I've been talking about in the last lecture. Last lecture we talked about how to introduce the line defect, okay, and how to and the surface state for 2D photonic crystals. So for line defect, it's very simple. You just remove the one column. It's just remove the one line column, something like this. Because due to band gap effect, the wave cannot propagate along horizontally. It only can propagate vertically. So they can form the waveguide structure. This is for this waveguide structure. Another is just for this surface state. Okay, if we truncate the waveguide as its boundary, okay, we cut the half typically. We can cut it half. We can have a different method to truncate. And this situation has some surface state. This is a very standard dispersion diagram for this kind of photonic crystal structure. It has a different region. Okay, the first letter it means air. The second letter means crystal. The E means the extended. D means the decay. Okay, and this region, because this band gap, the original photonic crystal, this extended in air, or decay in photonic crystal. Okay, I mean the wave will extend in air region or decay in photonic crystal with band gap. And this region is extended in air and extending in crystal because there's a allowed state in photonic crystal. This is air line, okay, and the right hand of the air line, this is guided mode. This is guided mode. The guided mode in the photonic crystal, they decay in air and then extended in the photonic crystal. Okay, decay air, extended in crystal. Okay, so at this band gap region, the first at the right hand side of air line, it has a surface state. Okay, I means the wave will decay along the two kind of. Okay, it's very similar to surface plasma. I'll talk about this later. Okay. In this next chapter. Okay, they decay along the air region because this is at the right hand side of this air line, so this is a guided mode. That means you fix the omega. You fix the omega, you see this is kind of like K value, okay? So this is a guided mode, so it's decay along air region. Another thing, this is at the band gap region, so it's decay in the photonic crystal. This is means of surface state, okay, something like this. Okay, this is something we talked about in the last lecture. Then I talked about this final difference method to this calculate the photonic crystal. Okay, because you have the numerical experimental about this part, we just split a Maxwell equation with TM wave and TE wave. This because it's a 2D problem, kz equal to 0. Then we can discretize this wave equation with a final difference tensor. Okay, this is easy. So how to calculate this band diagram? We will should discretize this unit cell, okay, with a grid, okay. But at this boundary, there's no unknown in here because I said this point equal to this. It has connected to this point, so unknown should be smaller than 1, okay, than the unit cell. Okay, this is a very important thing. If you add unknown and here at this boundary, you'll find that your metric will become ill-conditioned because this point can be connected to this point by the Bloch theorem. Okay, so this unknown should be at least 4 by 4, okay, point. Then you can establish a sparse matrix. You can use 5 points tensor method. Okay, at this boundary point, you should treat it at this point outside this unit cell. Use Bloch theorem. Then you scan the edge of the gray zone to get this dispersion relation. I have given a detailed document for you, okay, in this numerical experiment, and I share some code. Okay, I have shared some code to you. You can finish this part. If you finish this code, I believe you can know photonic crystal better. Or else, I believe you totally cannot understand this kind of a thing. Okay. Important thing is that how to treat the defect, okay, in a photonic crystal. This is a very tricky. Okay. So people just use called supercell method. The original problem is just the point defect in the infinite large photonic crystal. Just introduce one point defect. This problem can be approximated something like this. We use a supercell that introduce defect. You can see there's defect. But this kind of defect do not cover each other because the distance between here is very large. And this is a photonic band gap, so this wave will decay very quickly. So these two this is a periodic. This is a defect couple. So we can use a periodic boundary condition to study this supercell problem. Let me to draw some dispersion relationship. Okay, something because it also has a numerical experimental. For defect in 2D photonic crystal, okay, we use supercell. Typically 5 to 5 is can get better results. Okay, because I have written code by myself, I found 5 by 5 is good enough. Okay, I just remove this part. Okay, this is for defect. Okay, this is defect. Okay. Why you do this Bray zone? Because here, this is a periodic boundary condition. Periodic boundary condition here. This is periodic boundary. This is a periodic boundary condition. Okay, we call PBC. And this boundary. Okay. This periodic boundary condition. When you do this, you draw this dispersion curve. Okay, you find something like this. Okay, this original curve, maybe this top band. Okay, this is something like this. This is for defect state. So okay, this is maybe gamma, m, x, and then gamma. Sit down to draw this better. So this is gamma, x, m, gamma. So this is a Bray zone. I draw this Bray zone here. Okay, this is a gamma, x, m, gamma. So this is okay. This is Bray zone. So I just draw this edge was in Bray zone. Is the Bray zone region. You can see this is a defect state. The defect state, why the defect state is a straight line, is a flat. Why? Why the defect is flat? So that means the eigenvalue, the eigenfrequency is independent over this k. Okay, this is right because the translation environment or translation symmetry are broken in this defect, right? Originally, the translation symmetry along the x direction, along y direction. But when you introduce the defects, the translation symmetry was broken. So you can see here, it's a flat. That means you can do a projection. You can compress this to this point because everything are same. Okay, everything are same. So you can compress this. They call it projection band structure. Okay, called projection. You can do a projection. This is a rhythm. Okay, so we can return back to the waveguide. Okay, return back to the waveguide. You can see this is a supercell for waveguide. Okay, when you use the periodic boundary condition, okay, they can use periodic boundary condition here, also here use supercell structure. You can see there's many waveguide structure, but they are not couple each other because the number of cell here is large enough, so field will decay because it's a band gap with band gap. Okay, so when you do this kind of structure, you also can get this, gamma, x, m, gamma, but you can do a projection. Okay, because only along this direction there has translation environment. Along that direction, does not exist. You can do a projection. So finally, you get something like this. Okay. You get the dispersion something like this. Okay, this case only along this direction. Only along this direction. That means another case along that direction does not change this curve. We can do a projection. Let's do a projection. This is a same thing. Okay, this is something I talk about in 2D photonic crystal. 2D photonic crystal. So today we talk about 3D. Okay, 3D photonic crystal. 3D is more difficult than 2D, but maybe it's more interesting. So we see the 3D structure. Okay, 3D photonic crystal structure. I like to see this diamond. How to enlarge this? I can do this. Okay, before I talk about this, I just talk about something, analogy. Why I talk about this? Okay, so everyone knows that, we should know that electronic band gap, they are invented or they are studied as much sooner than the photonic crystal. So people study the solid state physics, know the electron band gap, then people study the photonic crystal, know photonic band gap. So at that time, maybe 15 years ago, maybe 10 years ago, I can't remember, people studied how can we realize a complete 3D band gap, okay? How to realize 3D band gap, okay? I mean, completely, okay? And that is a very hot topic. It's not easy. At that time, people ask how to realize 3D photonic band gap. Photonic. So people just borrow the idea, how to construct the electronic band gap because they are very similar to each other. I talk about this because everyone knows. I draw this equation. Right, I wrote the equation many times, but it's important. I wrote this again. Okay, this is a Gaussian equation for Maxwell equation, right? Another equation. This is phi, V phi, E phi. This is for Schrodinger equation. This is for photon. This is for electron. Okay, so we have analogy. Very important analogy. Okay, so that means for this operator, this Hamiltonian operator in Maxwell equation analogous to this operator. Okay, this is for Schrodinger equation. This Emerson one, the analogous to the V. This is omega similar to E. Okay. So everyone knows that we know how to form the band gap. That means in a lower band or in a lower frequency, the EM energy will concentrate on the dielectric region, right? Because Emerson is larger, omega is smaller. Okay, according to a verification principle. Okay, it's quite similar to electron. If Emerson is larger, the V is small. Okay, so electron typically initially they stay at the lower potential region. Then when the omega is larger, it means the electron has a higher energy, it can jump to its high potential region. It has a barrier that can jump to a high potential region. So they're quite similar, okay, quite similar to each other. So at that time, people just think that if we know some knowledge in the electronic band gap, we can benefit this knowledge and we can construct the photonic band gap. Okay, this is analogy. This is a very important idea in physics society. Okay, so physicists like learn a lot of difference and find a similarity. Okay. So this is important. So people just study it called diamond structure. Okay, why diamond structure is very popular? This diamond structure. Okay, I'll talk about this later. Why is it popular? Everyone should know. Or do you know why it's popular? The diamond structure in semiconductor physics. It's for silicon. Silicon is diamond structure. Gallium is diamond structure. Gallium arsenide also diamond structure. So this is very fundamental. It's also for carbon, like diamond, for diamond material. Okay, for diamond material, silicon material, gallium material is diamond structure. Okay. They have a band gap. They have a band gap. Okay, so people just said, oh, if I can use this similar structure to construct a photonic crystal, it also has a band gap. This is a basic idea. Okay. Let me to talk about this structure. This structure is a little bit complicated. So I found a very good material in internet. Where's the internet? This? Oh, that's good. This is by the professor Verma. Okay, they upload this PPT. Okay, I think it's good. Okay, okay, you can see this is a unit cell. Okay, this is a typical unit cell. I give the intuitive picture. This unit cell called cubic. Okay, you can see it has a 8 point and this cubic structure. They call it cubic. Then they can introduce another, maybe different atom or different letter, maybe a same or not same. You can introduce. We call the body center. Okay, body center. Here, this is very important, very famous, called face-centered cubic. Okay, you can see here, this has a atom, maybe a ball. You can understand photonically, so like a dielectric ball. Okay, you also can understand in semiconductor like an atom. Okay, or maybe ion or something. Okay, they have something like this. Okay, in a corner. Okay, and they introduce some face. You can see there's another atom. It has a face and a face. You can see 6 face. Okay, they call the FCC. We call it FCC, face-centered cubic. This FCC structure. Okay. So how about diamond? Diamond is just 2 FCC structure. Okay. So you can see this before. You can see this is a FCC. Okay. It's an intuitive picture. It's better. You can understand it better. Okay. This is corner. It's blue. You can see this is the face center. Okay. This is maybe yellow. Something. This is the face center. FCC. Okay. We call it FCC. Then we have diamond. Diamond is just 2 FCC structure. It's 2 FCC structure. Okay. The yellow one is 1 FCC structure. Then they shift. Okay. They shift. It shifts along this direction. Okay. You can see this shift. This ball shift to this, as here. This ball shift to this. Okay. Okay. This is diamond. Diamond is just 2 FCC structure. Okay. Go to next page. Okay, this is better. You can see. Okay, so you can see this 8 carbon atom at the corner. Okay, this carbon atom at the corner. Okay, and the 6 carbon atom at the face. Maybe this is 6 at the face because we have 6 face, right? F 6 face. Then they also have the 4 internal carbon atoms. Okay, forming a tetrahedron. Okay, they shift this carbon atom to this. You can see same direction and shift, add them together. This is a diamond structure. Okay. Okay, this is diamond structure. This is 2 FCC structure. Okay. How to understand the structure? We can see here. This is projection. Okay, and projection is 3D. So this is 2D. You can see what happened. It's interesting. You can understand. Okay, you can see here. This is the bottom. Okay, it has 4 corners. Okay, 4 corners. One is face center, right? This is the first layer. Okay, we go to the second layer. Okay, this second layer, this 4 for face center, right? It's 4 face center here. As this is 4 face center projection. Okay, along here. Okay, how about this black one? Okay, you can see here. This black one. Okay, this black one. This another black one. This is a projection. This is a projection. Okay. You can see a different color means different layer. Okay, different color means a different layer. Okay, you can see the red. This is a yellow color. Is the bottom layer. This is a green color. This means the face. This is a face along this region. This is a blue, and this blue part is just 4. Okay, additional one. Okay. This is the full picture for the diamond. Okay. So if we consider this atom is carbon, you can see, how about this navel of this carbon atom? They have 4, right? 4 navel, right? They call it pi bonding. Okay, they have pi bonding. Only consider 4 atom very near to this. Okay, so everyone know the carbon or silicon. Everyone know the outermost electron, the number of outermost electron for carbon 4, right? So each carbon should be connected to 4 carbon to make a very stable structure, right? Forms covalent band. Okay, so you can see this carbon, like every carbon, they have behind the periodic. Every carbon connected to the 4. Okay, another carbon is like form a valence band. Okay, forms a covalent band. So this is a diamond structure. You can see the diamond structure has some different layer, and each layer has different position. They are interleaved. Okay, you can see they are interleaved. Right? This is a feature. Remember, it's a feature. Okay. Interleaved. So I return back to my lecture note. Okay, this is the diamond structure. This is diamond structure. Okay. How about the blue one just cubic. We call it, this is blue plus red is just FCC, phase center. Blue red just plus pink is diamond. Okay, this is just unicell. Okay. So how about this? It's a primitive lattice. Primitive lattice. Okay, this is unicell, not primitive lattice. Primitive lattice is a minimum unicell. Okay, for this phase center, phase center cubic, this is a primitive lattice. Okay, this is red region. You can see they connect to this. This point connect to this here. This phase center. This another phase center. Oh, sorry. This phase center. This is this maybe another phase center. You connect that. This is called primary cell. This is primary cell for this FCC structure. For diamond, for typical FCC structure, only have one atom. For diamond, we have two atoms. You can see. These two atoms just within this FCC structure. Okay, let me repeat that. This is a unicell. This is a primitive lattice. This is a primitive lattice. Okay. You can see this is a primitive lattice. So this is similar. This is maybe A1. This is A2. This is A3. It's a primary vector. We control this prime structure because the diamond constructed by the two FCC structure. I said, right, the original FCC then shifted by the 104. So they have two atoms within this with one primitive cell. Okay, this is two atoms. These are two atoms. Okay, this one atom here, another atom here. This is two atoms within the primitive atoms. Okay. So for silicon and diamond, maybe gallium, the two atoms are same. Okay, just same carbon, same silicon. And for GIS material, they are just different elements. Maybe this is a gallium arsenide, this is arsenide. This is gallium, this is arsenide. Okay, it's something like this. Okay. This is the basic idea. So why this structure is important? Because people found, oh, first thing, this structure is very stable in electronic system. Another thing, their structure always has band gap. Okay. So people said, oh, if we can construct the photonic structure similar to this structure, it should be had a band gap. Okay. So you can see here, one atom or one carbon atom has four neighboring hoods. They forming a chemical bond, right? Chemical bond. So how about electron distribution? So electron distribution, I mean the wave function. Okay, this around this point, also around here, right? Because it has a chemical bond. So electron also move around here, also move around here, right? Okay, that's very good. Why? It's very good. So everyone knows that. Why is it very good? So everyone knows that. So sphere. So we know that if you split a band gap, maybe I just show this picture. FCC. So everyone knows that for 2D photonic crystal, okay, this 2D photonic crystal. Okay, I just show. They have TM band gap, right? Because it's a column in here, they have TM band gap. If I connection, I do the connection. Okay, I do the connection, something like this. That's connection. Draw here. Okay, better. Okay, they have T band gap. Right. So how to form a complete band gap? Just wing plus ball, right? Wing plus cylinder. Okay. So for 3D, I go here. You can see this structure. So this is very special. Okay. Where's the ball? Oh, this ball. This is the ball, right? Where's the wing? This wing. This is a chemical bond. Okay, this is a chemical bond. It's a chemical bond because electron can move, but because it's a chemical bond, it move around. It can form a bond. Okay, okay. So this is an intuitive way to understand the structure. Okay. So this is one insight. Another insight, because they have the ball and they have the cylinder and the wing. Okay, they have band gap. Another, this is diamond, it has like a typical material, it has a band gap. Another thing, how to open up a band gap? For 1D crystal, for band up open at the Brazon edge. Okay, Brazon edge. This is important. I draw this picture many times because for 1D photonic crystal, everyone should know that this is K, this is omega, this is dispersion relation, this is dispersion relation. I do the periodic expansion. Okay. So open up at here. Here we call it what's the name? Bragg plane, right? We call it Bragg plane. Okay. So because it has standing wave point, this is omega equal to ck, this is omega equal to minus ck, this is standing wave point. When you perturb this structure, this is free space. When you perturb this structure, the band gap will open up. Okay, will open up. Okay. So this is a region band gap will open up. Okay. But difficulty is that for 2D photonic crystal, okay, for 2D photonic crystal, what's the difficulty? Why the band gap is difficult? For 2D photonic crystal, I draw this picture, but Brazon change, right? Brazon change something like this. It's gamma x m. Okay, go ahead. Gamma x m gamma. Okay. Why I draw this picture? Okay, something like this. I just draw this picture, right? Because at different key, at this here, this is band gap. And here, this band gap is around here, and here, band gap here. So that means the difficulty is here for 2D photonic crystal, different direction. The band gap location are shift. Okay, are shift. It are not the same. You can see, this is the band gap smaller, this is higher, this is smaller, maybe in the median. Okay, so how to find a common band gap? Just you should increase the permittivity. Increase the permittivity, increase the high contrast, right? You can find it's a common. This is a common band gap. Okay, this is a common band gap. Okay. So this is a difficulty. So for 3D problem, if the edge or this Brazon, I mean the edge or Brazon has the same magnitude in all the directions, like a sphere. Okay, which kind of Brazon? Free space, right? Free space is a sphere. The Brazon edge is sphere. Right? If you give a virtual periodic boundary condition, it's similar to sphere. Okay, but it cannot. But typically the band gap in different direction, the difficulty that band gap in different direction has different frequency. Okay, has different frequency. Just I draw this 2D picture. Okay, just I draw this 2D picture. Okay. In different direction, the band gap will shift. Okay. So this is the problem. So how to construct a Bragg plane? This is similar to sphere. This is better, right? Because in sphere, it has same frequency. It has same frequency. Okay. So diamond structure. This is a Brazon. This is the first Brazon or FCC. You can see this is quite similar to a sphere. This is a Bragg plane. Okay, they call it Bragg plane. You can see many Bragg plane. You can see it's quite similar to a sphere. This is the reason why it has a large band gap. Okay, because it has similar to a sphere. Okay. This is the reason. Okay. So, but typically there's no 3D crystal with a perfect sphere. Okay, but this FCC or diamond, this is nearly a sphere. It's nearly a sphere. So this is an open up a band gap. So everyone should understand what's the difficulty for the band gap. Because different direction give a different eigenfrequency, they are shift. If the eigenfrequencies are same, it's very good, right? It's very good. Okay, like I draw this ideal case. What's the ideal case? It's a 3D problem. It's ideal case. X, Y, Z. Okay, this is one ball. It's another ball. Okay. Okay, this is band gap. Okay, if this lower frequency, the higher frequency, this band gap. It's very good, right? It's a very good situation, but it's quite difficult. Quite difficult. So diamond is very similar to a ball. You can see similar to a ball. This is a photonic band gap. But how to construct in photonic crystal? We have no vein, right? Vein is difficult, right? Just enlarge the size of the sphere, make them overlap. It provides a continuous channel. Okay. So it just They just use sphere in this picture. For photonic pictures, I use sphere, but I enlarge the size, make every sphere overlap. Okay. They can provide the channel. See this picture. This picture. Okay. Can enlarge itself. So sphere and diamond structure overlap each other, provide continual channels. So finally, band gap open up. This is the first one. It's pioneer work. First one, they demonstrate you this structure can get a completely band gap. Okay. So this is a breakthrough. Okay. So all the idea just from the electronic band gap. Okay. Electronic band gap. It's first. But this theoretical work cannot fabricate. Cannot fabricate. Okay. What's the first fabricated solar cell? It's by Yablonowicz. Okay. Yablonowicz, this is the first work to fabricate just electron experimental demonstration for this 3D photonic gap. They can realize. Okay. This is by Yablonowicz. Okay. They call this Yablonowicz. Okay. Yablonowicz. Okay. This is structure. Okay. This structure is interesting. So it just drill. Okay. You can see this is similar to 2D. It's a column. It's a column. Hexagon structure. Similar to 2D. They drill. The drill is this hole. Okay. This is a hole. They drill this hole, but not vertically drill. This oblique drill along the three direction. Okay. Drill that. Something like this. Fine. They can form a band gap. So Yablonowicz also this structure also can be understood. This is diamond-like. Okay. This diamond-like structure. Okay. This is something diamond-like structure. Okay. Because why they should drill a different direction. They should drill the cell in different direction. Because diamond, remember diamond. You can see the diamond, they have interleave, right? This every position are interleave, they have projection. So you must draw a different direction to touch this point, similar to that. Okay. So this is an important thing. This is also a multi-layer structure. But I'm not quite clear about Yablonowicz's idea. Maybe he knows this better. Okay, he knows this better. I'm not quite understand this idea. But this is the first one for experimental demonstration. So they also a pioneer work. But this structure, I think, is very popular and easy to fabricate. They call it wood pie. Okay, wood pie. You can see this structure. This is very interesting structure. First, they are orthogonal to each other. Each layer orthogonal to each other, right? Why? For 1D, we know Bragg scattering, right? A, B, right? They can do a band gap along one direction. So for 3D direction, we must orthogonal each other, right? According to Bragg scattering. Another, they shift. They have offset. You can see the top horizontal layer and the third horizontal layer, they have the offset. They not align, but offset. Why? Diamond. Yeah, diamonds are interleaved. Every atom are interleaved. Remember the projection picture? It's also from diamond idea. So, how to open up our band gap? Use orthogonal direction and offset. Okay, they can open up a band gap. They can open up a band gap. So, I like to mention about this idea again. This idea is interesting because there's many recently work also use this idea. Okay. This is sphere. Z is sphere. Spherical grid. I have added this. So why this idea is simple? Graphene. Right? Graphene has no band gap, right? How to open up a band gap? Graphene, this is the version for graphene. Right, this is for 3. Maybe this is Kx, Ky, this is omega. Show this better. Why? I said there's not too much new idea. Everything just repeat original work. This is the graphene, right? Graphene is direct cone. It's a cone. There's no band gap. Okay, for graphene. How about the structure for graphene? Something like this. I draw this. It's carbon atom. Carbon atom. how to open up a band gap? Stack. Remember, it stack different graphene layer by layer. It stack the same atom? No. Right, it's offset. It's offset. Well, its multi-layer is right, but it's offset. Oh, no. And this graphene, this first layer and the second layer, they do not overlap, but shift. Right, this is original idea. The same thing. So, it's something like this. It shift. It shift this atom. I cannot draw this better. Sorry. I use another colors. It's graphene. It's graphene. Fine. So when you stack them, they shift half. Okay, they're similar to this. So you must, when you shift them, a coupling, if they do not shift, they only coupling along this direction, but you shift, the coupling become, many atoms will couple each other. Okay, according to couple theory, the band gap will split. If do not shift, this one atom only connect to 3, right? According to time bonding scale, okay, I will consider the nearest level. But when you shift, this atom will connect to many, right? Smaller, higher, this coupling become different. Okay, this coupling become different. Okay. So this is the same idea. Okay, to open up a band gap for graphene, it just offset this graphene layer. Okay. So this is about this wood pie. This wood pie also very famous. I believe this person fabricate this person and will become very famous. Okay. This is maybe this EBM. I'm not sure it's how to fabricate. It's a very nice structure. They can be realized in experiment. Okay. Then another idea, okay, is from a 2D. Everyone know 2D for rod has a TM band gap, for hole they have TE band gap. So they do this, add them together. Okay. So for first layer is a column. Okay. Then is a whole layer. Then column layer, whole layer, but shift. You can see, a shift. You can see. Column layer, whole layer, but this column region is not same with this. Okay. So very similar to wood pie. Wood pie also an offset. It also has offset, but this is still supercell. Each one by the column and the hole. Okay, or the column and the hole. Okay. This is from a 2D structure. They also have a band gap. Okay. So it has a basic idea is just use different layer and shape them each other. Okay, with this dielectric sphere or cylinder, and with a hole layer is a vane. Okay, this is the basic idea. You can see this structure also interesting. This is for 3D photonic crystal. Okay, so we have a break. So any question about this part? For this structure? Okay, I hope you, when you can discuss with your friend, you can know the diamond well. Okay, what's the diamond structure? WP, X W. So this, you can see the spread region. Along the edge, they draw this kind of very common. It's a Brazil region. Before 3D FCC lattice, it's a Brazil regions, very common. Some, I believe there's a lot of books that are not talk about this because it's very complicated. I just give an intuitive picture. It's the FCC. They cut the bar plane, you can see they cut the bar plane like this. Okay. So this diamond structure. Okay. I think everyone should remember this diamond structure. This is very important. Let me go on. For typical structure to fulfill this 3D completely photonic band gap. Okay. At that time, it's not easy. So it's a difficult task to completely band gap. So quite similar to 2D and 1D, it also has a defect, like point defect or line defect. This is everything are same. Everything are same. For 3D also has a defect. You can see this structure. Okay. Let us to take a look at this structure again. This is the first layer is a column. Okay. A second layer is a whole layer. It's a whole. Second layer is a whole layer. Okay, it's a whole layer. Then a column layer and a whole layer. Okay, it's something like this. But they are offset. It's offset of these two layers. It's offset. This is this structure. Then we truncate. Truncate structure. Okay. This is a projection wave. Okay, you can see here. This is column. You can see this is cross section. This is a column. Okay, this is a hole. This is a hole. Okay, between the two columns is a hole. This is a column. I remove this one column in here. I remove. Okay, I'll introduce a point defect. You can see this is point defect. This is a monopole mode, right? Very similar to 2D photonic crystal. Okay, they tell you, oh, this 3D, this is 2D. 2D, this is the infinite length. I remove a one maybe hexagon column. I remember this. Okay, this is dipole mode. This dipole mode is quite similar to this 3D dipole mode. Okay. Monopole mode, sorry. It's monopole mode. Okay. So why is the monopole mode? When you remove one column, when you remove one hexagon column, you decrease your permittivity, right? When you decrease your permittivity, you increase the eigenvalue. Okay, so this is this is eigenvalue. If from lower frequency, I introduce defect, right? According to our verification principle. Okay, and this back. I say again, I decrease the permittivity. Okay, because initially it has a dielectric column. I decrease the permittivity because it becomes air. I decrease permittivity, I just increase the frequency, right? So this is air defect region. Okay, it's from the lower band. And this lower band is monopole mode, so this is similar to monopole. Okay. Another, we can increase, okay? We can increase the column, you can see this is increase the column. Or increase the size. Increase the size of a column is similar to the increase permittivity. When you increase the permittivity, just lower the resonance frequency. Okay? Lower the resonance frequency. Oh, this is band. Another band. So this eigenmode and this defect region is similar to that. This dipole mode. This dipole mode. This is all maybe degenerate. Also degenerate. Okay. This is just a fully verification principle. Okay. Everyone knows that for band structure from lower frequency to high frequency, the monopole mode, dipole mode, quadrupole mode, right? When you introduce the defect shape should be very similar to the eigenmode shape. Depending on this is from the top band or from the lower band. Okay. This is just verification principle. Verification principle. This is a TM like because this is a column, right? I remove one column, I increase the column. Okay. We also can enlarge the air region, enlarge the whole region. Okay, enlarge the whole region. It's TE like. But enlarge the whole region, you can see this is quite similar to 2D photonic crystal. Everything are same. So this is 3D photonic crystal. You can see the eigenmode in defect is quite similar to 2D photonic crystal because they has a stack stack column and a hole together layer by layer. So this is a reason. Everyone should understand this picture because I have I give you an assignment about this, right? I just want you to understand this air defect, this dielectric defect. Why this dielectric defect eigenmode is similar to this? Okay, this is dipole mode here. This is a monopole mode here. It's lower band. So this is a reason. This is a reason. So for 3D, for example, everything are similar to 2D. You can see everything is similar to 2D. Depending on how to understand this. Okay. Everyone. So this I draw this many times. I draw this band diagram, right? I said if you has this right, this is a Gamelin equation. Then I do this Gamelin test. I do a Gamelin test. C square HR. I do a Gamelin test. C Then I use integration by part. Integration by part. This cell, I just copy. Okay, so finally, I get this very famous equation. This delta H equal R. It's a square epsilon R to the dr and over H over R. Okay. From this equation, we can draw this very easily. It's omega. Okay. Okay. This is the band gap. Okay, this is original lattice. So when you increase your omega, okay, you just increase the permittivity, just decrease the omega. So it's something like this. This is ins. This is this. Then something like that. This is decrease your instance, just increase your omega. Increase. So this is the mode, is the monopole mode. It's lower frequency, this is diaphragm. So this is the reason why you make it each other. For the numerical experimental, I send you also let you to draw this defect mode, also can find the similar thing. Everything. This is dipole mode, normal kind of thing. So this is defect. You also can introduce a line defect. Okay, remove one call, remove this top wheel, remove one line, remove one line. Okay, you remove. So it's quite similar to different boundaries. I mean, for this line defect for this structure, for this 2D, for this 3D structure, when you remove one column, the wave will confine. Maybe this column along Z. I remember along Z direction. This still confined along X and the Y direction. Okay, still confined along X and Y. I just remove one column. Okay, so this is a line defect. They also can, similar to that, we also can remove all the column. It has a 3D photonic crystal, similar to 2D photonic crystal. Okay. It's quite similar. But here I want to mention an important concept called slow wave. Okay. So there's a point at the edge of this band. I mean here, okay, here, maybe here, you can see the groove velocity. At this edge, okay, at this 0 or 0.5, this edge, okay, this normalized wave vector, this edge, the groove velocity is equal to 0. So this is a slow wave. It's a slow wave. Okay, it's a slow wave. When you do a slow wave, you can has a lot of application. You can do some delay line. You can compass. You can compress the pulse. You can compress the pulse. I can do some distortion management. Okay, it's a slow wave. Here, there's another interesting structure, right? First thing is just I remove all the column. Or maybe I'll remove one column. Okay, I do the waveguide line. Okay, I can do the waveguide. Well, this waveguide, this waveguide is only confined along this direction. Okay. For this direction, it also can leak up, right? It can leak. There's no band gap. But here, it cannot. Okay, it's different thing. Right? Because it's band gap here, also band gap. Only this direction. That means, let's see, this structure, I just move this column, I just move one column along it. Okay, this is a guide. Okay, this is a guide. So along the Z direction, along the Y direction, this still has band gap. I just move. I move still they only can move along X direction. Okay, it's similar to that. This is different. But this is just define out how to confine your field. Here, I want to mention about another concept they call coupled cavity waveguide. Okay, this is a coupled cavity waveguide. Okay. They do not remove all. Okay, I can remove all the maybe cylinder. I can remove all, but I also can keep some to make this a cavity. This is a cavity. This cavity. Cavity. Okay, but their cavity are coupled. Okay, they couple each other, so they also can propagate the waves. Okay, they similar to the electromagnetic. They similar to the some loop. Okay, inductor loop. But to inductor loop, they couple each other. Wave also can propagate, or some cavity. When they do this kind of thing, they couple each other. Okay, I just draw this picture. What's the name of a coupled cavity waveguide? The coupled cavity waveguide. This is a new coupled waveguide, coupled cavity waveguide.
Just like the top of the waveguide. Just similar to the EFP, grading on top of the waveguide. There's a grading and also the waveguide. And this one is similar.
It's similar?
Yes. Because the grading helps you to just give you resonance, just like the pen here.
Yeah. This is let me to illustrate this concept. What's the difference from? I'm moving something like this. Okay. This is a cavity. It's similar to cavity. Okay, this is a cavity. This is a cavity. Because it only has one column, so it's a field that not decay to zero. They will couple. They will couple to each other. They will couple to each other. So they are coupled, they can propagate. So I use maybe red colors there. This cavity, this cavity, this cavity. The field will couple each other. Can be coupled to each other. Because they are not decay too much. So if I change to this, you can see what happened. What's the difference, fundamental difference? If I change to this, okay, if this, the coupling becomes weaker, right? If we increase more, they have band gap. They cannot couple, right? The couple is weaker. The couple is weaker. The couple is weaker. Okay, this couple is weaker. Okay. So you can depend on your distance or this defect, how many cells here. So this is a way to understand. It's called a couple. They can propagate all this structure. This is land defect. Finally, I think this is the most difficult part. This is the localization and the surface. I mean the surface state. This band diagram is a little bit difficult. So what's the localization and the surface? Okay. First, we see how to truncate this photonic crystal. When you truncate the photonic crystal, you can just use the full row termination. I mean the outermost layer just full row. Okay, that's full row. It means the original just like the original. Okay, that means truncation something like this. It's truncation like this because this is truncation. No, above the layer this air. The truncation is used called full row termination. Just row. This kind of truncation. This is a very natural truncation because every periodic structure is finite. Right? This is a natural truncation. You can see it's full row truncation. You can see they have surface state. I mean this state decay along air, also decay along photonic crystal. Okay. You also can use this called a half hole termination. You can see they add a half hole in here. This thickness is half of this thickness. So this thickness at top is half of this thickness. Okay, it's a whole layer. That means the thickness at the top layer is only has half of thickness here. Okay, it's called a truncation here. It also has surface there. You can see. You see the decay along crystal, decay along here. But this is a band diagram. This band diagram. First thing you can see this band diagram. How about this airline? Okay, this airline is airline, but why is not straight? It's a curve. We have something curved. It's interesting. First, While you truncation your photonic crystal along z direction, the translation symmetry are broken. But x and y, they are still conserved. Okay, I mean along x and y, they are still a periodic structure, but along z direction they are truncated. So it has a gamma m k gamma in here. This is along the 2D Bragg zone. Okay, along the 2D Bragg zone. This is the first thing you should understand along 2D Bragg zone. Okay. Now how to understand this? Okay, I need to explain this better. Why an airline something like this? So use this. Why an airline? This is a key. This is omega. This is similar to I can't remember. Let me see what's the name. The name cannot be changed. You know, a gamma mx. This cannot be changed. This is this is well you should use this. Cannot be changed with other letter or something. You must use this letter. This is a gamma. We call it m. Now I do this key. Oh. I do this, they call it key, and they call it gamma. This is KB, Bragg. Something like this. So the airline, they draw this airline, something like that. First thing we should understand why the airline is something like this. This is airline. This is a little bit strange. When I read this figure, I also found this a little bit strange. But when I think about this is a Bragg zone. I draw this Bragg zone region. Okay. This is hexagon. This is hexagon. So this is a Bragg zone region. This tau, this k, and n. I call this is a kx, kb, and kx. This is around this is k, g, y. This is m. This is called kbx. Okay, this is a Bragg zone. First, we see this curve. Everyone know the KB is along the x-o-y direction is similar to tangential vector, right? This is z. Okay. This is x, this is y, this is z. I truncate. This is truncation direction. I truncation that is z direction. X, y is still a periodic. I truncation. Okay, y truncation, you can see the tau m. Along the tau m, I mean the k square equal to k rho square plus kz square. If k smaller, this k0, this k smaller k rho square. Okay, if k0 square is air, smaller than k rho square is guided mode. It's guided. Okay, so air line is just something k equal to k rho, right? Something like this. This is air line. Just make this kj equal to 0. So along the gamma and m direction, along this gamma and m direction, you can see first the kx equal to 0, kbx equal to 0. That means first is gamma m. I give you 2 examples. Understand. For gamma m, the kbx equal to 0, but the kby equal to I mean they have some along this ky. I mean they have some constant c equal to 1 equal to 1. This is this. Right? So finally the K rho equal to the KBY, right, equal to CY. Okay, so this is straight line. This is also straight line, something like this. But why the MK is so special? So MK is special. Why? Why MK is curve? How about the KBX? KBX is maybe I call it another constant called C1. It's C2 x, right? So I call C2x. But how about KBY? Huh? Zero? No, zero. Is zero? How about KBY? It's constant, right? Equal to this, I call it D. Equal to some constant D2, right? This is 0 point. This is 0 point K. So along here, the Y has a distance, right? It has something like a Y. So how about the K rho? C x plus, right? So this is the reason why it's a curve. You can see it has a constant here. So when you draw this, it has a curve. Okay. You can see this is just linear. They also this was a reason. Okay. So this is some reason. They draw this curve. They draw this curve. Because it's ky, this is a constant ky, but a linear chain in kx. So kx square plus ky square root is k root. Okay. So this is a reason. Okay. Along the k over gamma, this is also a line because this is similar to k root part. It's just along one direction. Right? I mean the kx and ky is along some direction. Okay, so it's just direct line. Another thing, because they have a breadth zone, they also periodically repeated. This line is similar to this line, So why they are folded back? Because this is from k to top. If from k to top, they are decreased. Not to top to k. If top to k something here. Okay, k to top something. So they are folded back. Okay. So this is you can say this is airline. This is the guiding mode region. This is the guiding mode region. This is the guiding mode region. Okay, this is the reason. But everyone who can understand this. I said this is why it's a curve because this ky is a constant and the kx is a linear change. Okay, so the k rho part, because I means the k rho square plus kz square equal to k0 square. How about airline? Airline is just line for kz equal to 0. Okay, it's airline because this is called airline. If the k rho larger than k0 is guided mode. If k rho smaller than k0, this is a propagation mode. So when the k0 equals 0, it's called airline. Okay, but this k rho part equal to kx square plus ky square. Okay, so here the ky square is constant. Okay, it's non-zero constant, and the kx square is linear. So this is the picture. You got this curve. But along here is from gamma to m. Okay, the x equal to 0, right? Only has a y, so it has a linear. Okay, because it's a 0 constant. It's similar to from gamma to k. Another thing, why it has a curve? Something because it's from k to top. From k to top, it's along this direction. If from top to k, this is a positive direction. From is something like this. Okay, this is folding back on here. So this is a guiding region. So this is a final picture. This is a guiding region. So you can see here. So E means extended. Okay, extended in air and decaying photonic crystal. This is a photonic band gap. Okay, extended in air, decaying photonic crystal. Okay, I mean the wave will reflect it back to air, but decaying photonic crystal is band gap. Okay, DE. Okay, decaying air, extending in crystal. Okay, this guided mode. Okay. Decaying air, extending in crystal. This is a guided mode. And the EE, that means both are extended air and the photonic crystal. It's allowed back. So the surface state okay. First, it should be located at a band gap, right? Because And they will decay along this photonic crystal region, right? So they should be located in the bandgap region. Another, they should be located at the right-hand side of the guided mode. Okay, the right-hand side of the guided mode. So this is the guided mode region. So they decay in the air. They can decay in the air. Okay, so this is a surface thing. Okay. So this air line is something very special. I hope you can understand after this lecture about this picture. Why they has curve, why it has
So in that case, actually if you make truncation for the computer, no matter 3D or 2D,
okay.
very simple 2D because you say understand. When they truncate, actually the properties of truncating have some features similar to making waveguide, if a waveguide.
But this truncation at the boundary.
Yeah, I know, but the same, they share the same thing is that the state is within the band gap region.
Yeah.
Just like the waveguide.
Right.
Because they.
But for surfaces, they do not. First, they should allocate in band gap. Another, they should allocate in the right-hand side of the waveguide. You can see. I go to here, so do not confuse this concept. You can see it here. This should be propagation. It should be airline should be something like this. It should be above this airline, or else it cannot propagate. Here is true, right? So maybe this for this you can see first it should be band gap because it decay along photonic bands. Along the air it also decays, so it should be along right hand side or guided wave. This is called surface link or surface link. There's a difference from the guided region. Okay, this picture is a little bit difficult to understand by yourself because I record the video for my course. You can also to listen to this again to understand. Okay, this is for this. I finished all this theoretical part. Okay, 1D, 2D, 3D. I finished this. Then I talk about this application. Okay, application for photonic crystal. Because I know that many students focus on the application or focus on some photonic crystal application. I like to talk about this application. First is the photonic crystal fiber. I know the Professor Kenneth, right? From Kenneth focus on this photonic crystal fibers. Okay, but let me talk about this. Don't try to tell me that this is only very successful application of photonic crystal. Photonic crystal, cannot be commercialized. Okay, most of the cases are failure. Except this. This will be successful. Okay, this will be successful case for photonic crystal fiber. So traditional optical fiber just use a core region and a cladding region. Okay, it has some guided mode. I give this. I return back to original guided mode better. I remember this. I mentioned about maybe here. I mentioned about this. What's the original guide? Yeah, here. This is the original optical fiber. This is core region, the cladding region. Right. They supported the guided mode. You can see that for TE mode, they have even mode, symmetry, and odd mode and symmetry. The TM mode similar, they have symmetry and symmetry. Because they are from different book. This book just align this book. It's from the Professor Zhong Shun in UIUC. This is from Professor Wen Shu. So I cannot find any book can show the TE and TM together. I don't know why. People just show the TE, and the TE is more fundamental. But it's similar. You can see even mode, odd mode. Okay, it's a confinement. Okay, so how about dispersion relation? Okay, this picture. Okay, there's 3 lines. One is for this N1. N1 is core region. This is for core region. This is for this cladding region. Okay, for guided mode is bounce between the region. That means because they should be at the right hand side. This figure, you can see this is. I use this figure is better. This is this is a key. What's the meaning of omega? This is omega. This is k. I will use this figure. Okay, I fix the omega. I give a k. Sorry, I did not. I use this because I didn't know this. Okay, no problem. Here I give omega. I fix omega. This k is larger, so this m. This is mode. This is for this co-region. Let me think about it. The candy is larger. Oh yeah, that's right. Fix the omega because omega is here. I just rotate that. Yeah. Fix the omega. The kd is larger, so it's this is guided mode because it's cladding, the cladding is decay. So guided mode is be bounce. You can see this bounce along. This is a two dispersion curve for this cladding region and the core region. Okay, this is a traditional guided wave structure. But this is just use this is k omega k. This is k omega. So it's a little bit different from different reference. So this is a traditional one. Okay. So modern one. This is photonic crystal fiber. Okay, typically it has 4 different types. Okay, photonic crystal fiber it has 4 different types. Okay, first it's called Bragg fiber. Okay, this is just 1D Bragg grating, AB, but they do a circle. Okay. So they similar to the PEC or PMC. They are confined, right? They have some mold in here. Okay, they can understand it as the wall. They cannot bump it. They just propagate around. Another, this is I talk about this because this is called a holy fiber. This is called band gap guiding. I mean this is the defect. This is the defect region. And this defect region, because this is a band gap, we will confine due to a band gap. This is a band gap guiding structure. This is this is a very useful or maybe advantage over the photonic crystal because it due to a band gap. Okay, maybe the loss of dispersion will be better than the traditional guide wave structure because it has a band gap. Okay, a wave will confine well and has a when you band this structure, there has no radiation loss or no scattering, okay, something like this. Another. This is a whole. This is index. They call it photonic crystal fiber, but this is index guiding. Okay, it's similar to the traditional wave guide because it's index guiding, similar to reflection. Okay. So I did not talk about this. I talk about this. They use photonic band gap. In the photonic band gap, they confine the structure. Another is just use Bragg grating. This is a traditional optical fiber. I use Bragg grating. Okay, and propagation. The Bragg grating, when you do a Bragg grating, you can see they can filter, okay, one frequency and totally reflect it back. Okay, you can see. This is called fiber Bragg grating. Called fiber Bragg grating. Okay, it has 4 different types. Okay, I talk about the type 2 because it has a band gap guiding. Okay, they call it holy fiber. It's a different type. The band gap guiding. A band gap guiding in a holy fiber. So important thing is that because this is a projection, okay, it's a 2D photonic crystal structure, okay. But there's the situation is here. Kz is not equal to 0, right? Kz is not equal to 0. If Kz is equal to 0, wave cannot be propagated. So it's not a 2D. A T and TM wave will couple. Okay, they call it outward plane. Not in-plane propagation. I mean, in-plane propagation, it means a wave vector only along this plane. Outward plane, it means all has some wave vector along this direction. It's called outward. Okay. But Kz is not equal to 0. When Kz is not equal to 0, the band gap will be narrower, smaller. You can see that. All right. So guiding the air code is important. The gap open when Kz is not too large. Okay. When Kz is not too large for the band gap. Okay. So for this figure, so problem is that first we use glass. We use glass and hole structure. Glass, how about refracting index for glass? Very small, maybe 2.1, 2.2, right? And then with the hole, do this. No contrast, right? No contrast. We know the band gap typically open up for silicon, right? Drill a hole. Okay, this has a large band gap. So when you use glass, the band gap is smaller for 2D structure. This is 3D because Kz is not equal to 0. It's become smaller and smaller. You can see this is the band gap region. You can see very small, very small. Not too large because the contrast is small. They use glass. Maybe I think why they use glass maybe cheap. I mean, stable. I think they use silicon. Use glass. Okay. Another, you should above the air line, right? Only this really useful. Why? This is not useful. cannot propagate, right? This is the airline, they decay in airline, not gold, right? They decay in airline. I mean, they decay in the hollow. They decay in here. Right? It's just confined at its boundary, but they not gold. Right? So only band gap above this airline. That means this very, very small region are used for the optical fiber. Okay. Right. This region, the wave decay in the air, right? Only confined in the boundary. They call this is surface thing. This is surface thing. If they have eigenmode, you can get the surface thing. It's not go. Okay. So I want to know the region, just very small region. Then I go down. Okay. So I see some eigenmode. This is very important. You can see this different eigenmode at different position. Okay. This is a different color. Red, blue, and red, green, and blue. We have 3 different colors. You can see this eigenmode. We draw that. Okay. This eigenmode. Different color. First, they denote a different symmetry. I talk about this later. First, we see this picture. Which one is better for optical fiber, for guiding electromagnetic wave? Which one is better? Which is best? Which is best? First one, right? This is worse, right? Because the EM will confine its boundary, its surface state, right? Loss is very large, right? Scattering, absorption is very large. They cannot guide it. Right? This confined in some air region is defect, but it also has, you can see, some hot spot. As this, all this only has this small region. But here is better. You can see, okay, it's a large region. Okay, this is the mode we want. Okay, this mode is red line. Okay, this is red line. This is the first thing. You see the different profile. Okay, so for optical fiber, I want single mode. This mode should be confined in this air region. Okay, and the field mode, cannot confine, and the A. If the A field is very strong, it's scattering or loss become very large. So this is the mode we want for optical fiber. This is the first thing. Another why symmetry is important. They said, this book said, okay, I don't know, but they did not give a case. They said different color, it means the mode has different symmetry, but only red color, the plane wave can be coupled to optical fiber. I believe for optical fiber, you use LED or use something to couple, right? Give a source to couple them. You should excite this mode, right? We discuss the eigenmode. And I said, for electromagnetic system, the system is fixed. You know eigenmode. There are many eigenmode. But when you do the excitation, you only excite a few eigenmode, right? Only the several. So different eigenmode, maybe some eigenmode cannot excite it. Why? I give you an example. This is a very classical paper. I assume the E field is polarized along the horizontal direction. E field, okay. This is different eigenmode, okay. The positive negative means a phase, or okay. You can see here the E field is along the x. I mean polarized along x. They cannot excite the band 3 because along y the E field are symmetric, right? E field is along x. I mean E field can be along positive x, along negative x because they're oscillation, right? So they can excite the band 1, band 2, band 4, okay, but not band 3 because band 3 they are asymmetric along y direction, but the E field along y direction is symmetric, okay, so they cannot excite band 3. Okay. This is the mode symmetry, okay. I mean that the positive negative because E field along the y direction are constant, do not change the direction, it's just even, okay. This is all. Positive negative, they cannot excite. This is the reason. This is why symmetry is important. I think the first paper is by the Jonah Poulos. When they calculated the eigenmode, band 1, band 2, band 3, then do the experiment. They measure the translation, they measure the reflection peak. They found only 3. They miss 1. Then they understand why this cannot excite because through the symmetry. So this for optical fiber also something. First, you should see the amplitude or E field distribution. Or you find this is good, but you also should be check the polarization, to see the plane wave can be inside that, or this optical fiber can be coupled to the plane wave. Okay. Why is this convention? Oh, maybe So this is a optical fiber. But in a real situation, so what's the difficulty here? Okay. So scattering and scattering loss and absorption loss due to a surface roughness is much worse for a mode concentrated on the surface than for a mode concentrated in the core. Okay, they said, okay, if the mode concentrated in here, it has some scattering absorption loss. Okay, so concentrated in the hole is better. Okay, this is the first thing. Okay, but the problem is here. So one could attempt to operate in the air core mode. Okay, I mean the E field should be concentrated in air core, but they provide difficulty in practice. Why? So because it has an imperfection, right? And fabricated, you can see this is real. You can see this is not periodic, not so good. Okay, it has a distortion, it has imperfection. When this imperfection, it makes this mode will couple. You can see this kind of mode. This mode very dense. You can see very dense. If you slightly distort this, they couple each other. Okay, so this is the problem. So currently, how to solve this problem? Just increase the radius, increase the size of the defect radius. Okay, you can see this mode can be separated better. Okay, just increase the size of this region. Okay. So this is currently a method to solve this problem. So this is difficult because the mode will couple each other. So you can see that photonic crystal is very nice. It's lost because we will assume the emission is lossless, right? Emission is lossless, no dispersion, right? But in real situation, they have loss, they have dispersion, right? They have imperfect fabrication of periodic. Maybe they weakly satisfy the periodic, they will perturb some mode. Okay, so their mode will couple each other. So it's difficult. Not be so easy. But this can be commercialized. You can find some, right? It can be commercialized. I'm not sure if it's commercialized. But people do not use this optical fiber. Right. They use the traditional optical fiber. Then I talk about this some application. Okay. Until now, we learned the band gap and the structure. Okay, we know the photonic crystal has a band gap, so they has do some reflection. They has a band edge. And band edge grow velocity equal to 0, so they can do some slow wave. Okay, they also can form some waveguide when you introduce some defect, right? Or become some cavity, use some point defect, right? They can do a cavity, do a waveguide, do a reflection, right? They have many applications. But we also can, combine this structure together to show some more interesting application. Okay. This is the case. Okay, you can see here. This is a line defect, right? This is a waveguide. This is line defect, waveguide. But here, this is a point defect. I just combine. I combine the point defect with line defect. What happened? You can see at some wavelengths. Okay, they call off resonance. You can see the wave cannot propagate to the output port. But at a resonance point, the waveguide, it guides the electromagnetic wave, and it couples to the cavity. Then the cavity will couple to the waveguide. You can see here, the transmission is a very narrow band. First thing, they have very good selectivity, and the transmission can be achieved 100%. Lossless case. Okay, this is called filter. It's narrow band filter. Okay, you can see the interesting feature. This is the waveguide coupled to this cavity and then coupled to a waveguide. Okay, coupled to a waveguide. This is called a narrow band filter structure. Okay, how to model this? Okay, maybe we have no time this time. I just mentioned about this couple mode theory initially. Then I'll talk about this in the next lecture. So how about this model? We call it temporal couple mode theory. Okay. This is very important. I know, this book is written by the Stephen Johnson and Jonah Paulus. This method, Professor Fan Shan Hui, Professor Stephen Johnson, Jonah Groff, they also use this kind of a theory to understand the physics. They use it well, even in solar cell. Okay. So temporal couple mode theory can be used to understand many different physical phenomena. Okay. This is, I think, the original researcher proposed this temporal couple mode theory is about the Haus, H-A-U-S, Haus. This is a professor in MIT. Okay. They teach the course with maybe they teach the course to Professor Fan Shan Hui, maybe Stephen Johnson, even Professor Wen Chu. They listen to this course about Haus. Haus proposes temporal couple mode theory to understand this. Okay, this is an intuitive picture. How about this temporal couple mode theory? Okay. First, this defect. Defect is the resonant term. Okay, you guys see this. This is a resonant term. This defect. This is the waveguide. This is a waveguide. Okay. So this is a resonant term. This is a waveguide. So for waveguide, they have incoming wave. Okay. S1 plus. Okay. Here we assume that only one mode in waveguide, only one mode in resonant, only one mode in waveguide. Okay. We can assume this can be generalized to many modes. Here is that one. Okay. It's incoming wave. The incoming wave coupled to this waveguide, okay, return back. Okay, this is an outgoing wave. Okay. Then this waveguide also coupled to this another waveguide formed to the outgoing wave. Okay, outgoing wave. This S2, maybe you can add another wave from S2. Maybe you can make it 0, no problem. Okay. You can add another wave, we also have incoming, outgoing. This is a picture. So how about this governing equation? First thing, you assume that the field in a cavity proportional to some A. The A is just given the amplitude and the phase. It's a variable. Okay. That means because it's a single mode, the electromagnetic field can understand A equal to some eigenmode. So it just use A because this theory is very simple. No field distribution, just coefficient, just an ordinary differential equation. Okay, just some coefficient. And no field distribution, so it's very simple. A in here, I mean A can be understood in amplitude or phase for some eigenmode. They have eigenmode. They use A. Okay, this is just number. Okay, so amplitude A square is the electromagnetic energy stored in the cavity. Okay, A is the amplitude, and A square is the energy. Okay, this is the first assumption. Another, just I said, this is a incoming wave. This is incoming wave. This outgoing wave. Okay, this incident wave. This reflective wave. Okay, this is another thing. So this is a couple more theory can be written as something like this. Allow me to explain this, and we can conclude this lecture. How is writing this? Okay, the dA over dt just means the change of EM field. Okay, change of EM field over this cavity. Okay, change of EM field over the cavity. The first thing is minus I omega 0 means, okay, first we ignore falling term. We ignore falling term. How about this solution? Just exp minus I omega 0t, right? This solution. That means the field will oscillate like sine or cosine wave. Okay. This is for the ideal resonant term, right? Just one, do not couple anything. Ideal resonant. Okay. Because this is the physical meaning of first term. It's oscillation as the sine or cosine wave. Another, the decay. Because the waveguide coupled to the, because this cavity comes to waveguide 1, also coupled to the waveguide 2. Okay, so they are decay. Okay. I mean, if I ignore this, ignore I omega A, just keep this part, how about the solution? Just exponential decay, right? exp or minus t over tau, right? Just exponential decay. So this is exponential decay in T1, tau 1 and tau 2. Tau 1 and tau 2 is a lifetime, similar to lifetime concept. The following two addition term, the coupling from the waveguide to cavity. Okay, that means when a waveguide gives a wave, it has affection to the cavity. Okay, that means they proportional to the S1 plus and S2 plus. Okay, see another coefficient, right? That means the coupling waveguide to the resonance also is a coupling from the waveguide to cavity. Okay, this is for cavity equation. Okay, not difficult. Another equation is just for waveguide. For waveguide, it's simpler. I mean, for waveguide part, the reflection wave or outgoing wave SL minus equal to some coefficient for the incoming wave. This beta L similar to a reflection coefficient, okay, and some coupling. I cannot see. I just go. Okay, this coupling from cavity to waveguide. This coupling from cavity to waveguide. Okay, this has gamma. Okay, this is a couple mode theory. But this you can see very complicated. Why? Tau 1, tau 2, alpha 1, alpha 2, beta L, gamma L, many unknown. Right. But in next lecture, I'll tell you that all these unknown can be reduced with two or three unknown with some electromagnetic properties. Okay, this is important. This is original one. But finally, you do some simplification. I just show this figure. This is the final one. You can see only has omega 0 resonance frequency, tau 1 and tau 2. Okay, only three. Tau 1, no other unknown. Because they are connected with each other somehow. I will show this in next lecture. Okay. So any question about this for this my lecture for this diamond structure and the optical fibers? Any question about this optical fiber and diamond structure? Okay. Any question? If no question, remember because I give your numerical experiment for this band structure calculation. I gave a detailed document. Okay, you should spend some time to realize this program. This is good for you. If you realize program, you can know photonic crystal very well. I believe. It's not easy. You can try. I share some code in this document, my code. Give a detail. You can read about it. To realize how to draw this band diagram, how to draw this band diagram with the defect and eigenmode, how to see this eigenmode. Okay. After, because the deadline is November 30, okay, for the deadline. After this deadline, I will share my code to you, okay? Because I have finished this code for this defect, for this band diagram. You can see this eigenmode, very nice. It's same with the textbook. Okay. I can share this code for you. The first unit give the 70% of this task. I will give a word. Okay. Not 100%, it's too difficult. If you finish 70% of this task, I will give a word. Okay. You can try your best to do the distortion, advanced structure calculation.